I believe you guys have been doing it.
Sir,
Yes.
can you
Oh,
kindly record the session for those who can't log in? Because I'm seeing that the attendance is poor due to the fact that people can't log in since they can't access the internet. And there's a simultaneous class that is being hosted for STEM Plan.
oh, but we're gonna be recording the session, Sianda. So it shouldn't be a problem, right?
Okay, thank you.
Yeah, yeah. Okay, guys. So let's move on. So the session is recorded. And obviously everyone will have access to it as before. And again, guys, if you're having any issues, email me. Don't 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 say nothing. Just say, sir, there's a concern. I will address it. You're not meant to be thinking about that. But that being said, I'm looking at the recordings and I see only like a few views. I've seen the latest ones is like 13 and 5. So I don't think people are keeping up anyway. But let's see. That's conversation for another day. All right. Welcome back to Mechanical Design 3. We continue with Spur gear design. The next chapter will be helical. That is a plan. I'm hoping I can cover what I need to cover there. After that, it'll probably be brakes and then clutches, and then we're basically done for the semester. And we've covered everything in that subject guide. Um, but for sure, when I teach it next year, there will be differences. But yeah, I'm just letting you know that. So I think there's like 3 sections left, and then we're done. Um, in terms of assessments, I mean, nothing was done. You've done tutorial, 2 tutorials. Another one will be done. And by next week, you must at least submit. Whose mic is it's to me? And please mute yourself. Thanks. Okay, I did that now. Yeah, got your tutorials, get that done. Um, there'll probably be 5 of them. So basically every week I'll be releasing one. And then after that, there's probably an assignment. I'm going to confirm with you. There'll be your midterm, your project, or 30% in your visa. So what's key, guys? Work on your project. If you have questions, ask me. I can assist you if you're going in the right direction or not. I'm able to do that for you. There's no problem. So work on that 30%. And once the midterm comes, you'll see everything will work out as long as just keeping up with the work. It's not tough, but just keep up. All right. So before I want to continue, I mean, last time we did the forces on the gears, which was fun. And we're going to continue this. But I just thought I'll introduce this quickly because I didn't mention it. But I wanted to just show you what the standard gate tooth looks like. It's a 14.5, a 20 degree, and a stub tooth. And just in terms of the geometry, I'm looking at it. You can see where that angle, where they talk about that angle, you see there, that 14.5, the 20, and that 20 over here. So they just I just wanted to show you guys. I mean, I should have done it before. We'll obviously be aware that the standard proportions for these gate tooths in terms of the dedendum clearance, working depth, hole depth, the tooth thickness. They're all typically times something of the module, which is coming from some table, which you've seen before. And then again, a way to quickly look at, like from a practical sense in terms of modules. And what you can see over here is basically 4 sections of gears, like for 4 different gears with 4 different modules, right? So what you can observe from that is that as the module increases, the size of the tooth also increases. Obviously, if you look at the equation, does it actually make sense? The module increases, then your teeth should decrease, or the amount of, oh, that's the amount of teeth, sorry. Yeah. So this is the size of the teeth. So also, if you increase the module, then your size of the teeth will get less. And if you decrease your module, then your size of the teeth would be more. So that's also another way of looking. But the key is the word module. Module, it takes a lot in terms of the geometric proportions for gating systems. But anyways, I just thought I'd just quickly share this with you so that it was done. Continuing with the lecture. So this is from Shigli. And I think where I actually want to start is over here, and I go back. There's something called dynamic effects. And we start talking about the forces and these dynamic effects, right? There's basically additional forces arising within the gear when they are meshing. And these include a few of them: errors in the tooth profile, the inertia of the rotating masses, the deflection of the teeth, there's inaccuracy in the tooth profile, and also the yeah. Um, what is key there as well, and I wanted to read this text, is that um, they state there when a pair of gauge is driven at a moderate or high speed and noise is generated, it presents dynamic effects. And they're saying, and that's the dynamic effects I mentioned before. And it says one of the earliest efforts to account for an increase in load due to the velocity employed, a number of gauges of the same size, material, and strength. Several of these gauges were tested to destruction by meshing them, loading them at zero velocity. Now, what is key here is that because, again, with design, there's always these factors. These are one of those factors, and it's something. It's basically a safeguard because they are unaware. They're aware of the other factors, but they have not quantified it to be exact. So, for us to quantify these dynamic effects, all we're doing is some kind of additional factor based on the pitch line velocity. You notice there it's FD equals that, something times FD. And there's a few for a different range of speeds over here. And again, tooth inaccuracies and deflections. So it's again another factor which you're going to add. But it is more than that. It's also important, and you'll see why. But we'll return to it shortly. So just remember the tangential load times by some other factor will result in some dynamic load, which we'll use as a formal assessment to determine certain things with the gear. But let's move on. So in terms of gear tooth failure, obviously we're designing, and we need to ensure that our gear has structural integrity, right? In terms of what is this? Our gear tooth doesn't fail. I mean, you might work in a company where this happens, or sometimes you're going to buy this off the shelf. But anyway, here's the awareness. Gear teeth are typically in two ways. One by bending failure, one by wear or surface destruction. With the other ones are breaking the tooth. And obviously the wear, there are a few factors in terms of the wear. Like, do you have to know all of this? No. What's key is understanding it falls in particularly in two different ways. What is, just to further expand on the bending aspect, so the gear tooth itself, right, is, if you think about a gear tooth, it's like a cantilever. Right? Let me just show you a gear tooth so you can actually see it. I had a picture here. Yeah, there we go. That's a cantilever, right? Supported on the one end, and it's like, yeah, and you have a force at the other end. And it's subjected to repetitive bending stress, right? As it's meshing, that's what's happening the whole time. So they're saying tooth breakage happens when the total load exceeds the beam strength, right? This is avoided by adjusting the module, the face width, and the fillet radius. Wear failure, that is when we as they mesh, and if they're not done right, obviously a complete surface layer will be removed. And so obviously to minimize that, we're looking at surface finish and proper alignment of gears. But like I said, these are the two main things. And based on these things, right, the failing and the wear, we're going to have some equations talking to them. So we're going to design our gear to check if bending is good and if wear is good. And I'll take you through that procedure. But let's begin with the Lewis formula. So the Lewis formula is basically the underlying fundamental, what's the word I'm looking for? concept for this. And basically it's applying the bending equation to a gear tooth, right? And you can see there he assumes that it will be a cantilever force on the end, does some mathematics, and then apply some assumptions as well. And we end up with the bending stress within the tooth is equal to 6 times Ft times L divided by B times T squared, right? So that's the first thing, right? So we can actually compute the bending stress within the tooth. Obviously, it's all there, so we can determine whether it's going to break or not. And obviously, I'm sure you're familiar with the M times, your Y over I. It's a strength formula, right, in bending. Okay. Also, with that, there's an it's kind of okay. I'm just going off the slides of Mr. Chipangu, but the what should have been shown is that from your Lewis equation, right? You actually can remodify this in terms of FB, and we can then call this your bending load. And then you notice that there are a few factors to look at. So this will be stress zero, which I'll tell you, there's your B, your width of the tooth, there's a Y, there's a KF, which talks about fatigue, stress, concentration factor. Obviously, we always know that's an important part. And then you also got the P, which is your one of your module, right? So just reverting back. Then based on that bending load, we've got a few things over here, right? And again, as you can see, it's exactly what I mentioned before, but it's all coming from this equation over here. So this is remodeled into that over there, and then that's now the load, which is obviously allocated to that stress. And then over here, what is key from this equation? This is the equation you'll be using the most, right? Obviously, we're going to go through this. When you look at your Lewis form factor, and that's to do with the amount of teeth in terms of pressure angle, you have to look at, this is the Y value. Whatever amount of teeth you have, whatever pressure angle you have, and you choose that Y form factor. Your module is your module, B is your width of the tooth. Then you've got your permissible bending strength, and that is coming from this table over here. So depending on what material you're using, right, I believe this is all tested and gives you these predefined values, is that if you have a look at, if you're using forged steel SAE 1020, this is quenched and tempered, heat treated, you pull a value of 124. Okay, so that's basically it. There's also a hardness value attached. And then what's main there is that when we are looking at basic gear performance or deem what is okay, the main criteria you're going to be using is that your dynamic load should not exceed the load capacity. So we are comparing two things. We're comparing FB, as mentioned just before, and your dynamic load FD. So we compare those two to determine whether the gear is suitable or not. This also serves the basis for something called the AGMA approach, right? Which is like the standard for designing gears. And that's what I like to at least get through with Spur gears. It's not tough, just a lot of stuff there. But anyway, I'll come back to that. But anyway, so that's what we're doing here. It takes us to the next section, and which is this method over here. It's basically the same, just a lot of factors we got to use. But what I'm going to do after this, and I'll tell you now, is we're going to do Lewis, and we're going to solve this example. And then I wanted to do afterwards, we're going to do where, and we're going to go through this, and we're going to solve that example. That's today's agenda. After that, we will look at the AGMA method, and we will go through that as well. But anyway, let's revert back. So key thing here, right? All what I said is that we are looking at this here. We need to find FP, we need to find FD. But let's tackle this problem here. Is that okay? Is there any questions before I proceed? You can just say no, yes, following, before I move on. Siabonga, Morgan, Tumi. Okay. Cool. Yeah, so let's begin with that example. Okay, so you can follow from a textbook as well. Obviously it's in the textbook. And once I'm done, I'll show you at what is the exam level. And if you can do that, you'll be sorted. So yeah. So it combines a bit of forces and a bit of gears. So I'm just preparing the question here, and yeah, we'll begin. Okay, let me just place it nicely. Yeah. Okay. Cool. I believe I wanted to sharing. All right, here we go. So again, the whole purpose of this thing is to determine. We're looking at FB, and it's again related to this dynamic force. Okay. And it's just a criteria we need to check if the tooth is strong enough. This is really over the top engineering, which you might not even do. Because probably what's more important is just choosing the right gearbox. But nevertheless, who knows? It might be these designing gears one day. I mean, yeah, with additive 3D printing. Anyway, so we have a pressure angle of 25 degrees, a 25 tooth Spur gear, having a module of 2 millimeters, and we have a 45 millimeter face width to operate at 900 RPM. Okay, what they want is FP, which is your bending load, and then they want the maximum tangential load and power that the gear can transmit. Okay, I'll talk about that afterwards. Some decisions, the gear is made out of that steel, and it has a fatigue stress concentration factor of 1.5. So luckily, this is typically given for whatever reason. So let me take you through the process. So the formula to begin is fairly simple. You have some options, and the formula is basically, I'll get it for you here now. Show you now. This one over here. Yeah, show you now. Your FB equals stress zero times B times Y times M. Okay, so I'll just make a note over here for you. So Y and stress zero, the allowable bending stress, is from tables. Okay, so you know you're gonna have to pull that from a table. Is that okay? So there's something I must tell you with this formula. So in this formula as well, do not worry about orders of magnitude. And you'll see what I mean. Okay. It's kind of like a direct plug and play for some reason. And I've not introspected this formula 100% myself, but I trust what they're saying. So let's get our Y and our stress zero from tables, right? So let me provide the table for you so you can actually obtain these for me. Let's start with stress zero, which is your allowable bending stress, right? That's of the tooth. Engineering has come a long way for you to just pull a value from a table. And this is table 11.3. Okay. Super simple. Okay. Yeah, so let's quickly do that. So can you guys determine what is my allowable static bending stress? That's the actual correct word, right? We're dealing with the SAE 1040 steel. So can you choose which one over here and choose my value? You can just shout out.
172 megapascals.
I appreciate that. Okay, so that's going to be 172 MPa. Straightforward, right? Then we go to the next table to pull up a Y, right? Let's quickly see. And this is the lowest form factor, right? This is to do the stress concentration thing. Just paste that over here. Just want to get that for you. Ooh, just do that. Okay, cool. Okay, my mouse is here. Just resume. Yeah, if you can see it, then you can obviously just tell me. Just want to get my notebook here. Cool. What is that value? Can someone tell me that value, please?
So I think you
Yeah.
have to scroll down a bit
Scroll
because
down.
Okay.
it
Okay.
says
Cool, cool,
25 teeth. Yeah.
cool. Okay. Cool. So we had 25 degrees. This one over here, right? I think it's 0.42. No?
0.42.
Okay. Perfect. Yeah. Now that's that. I think the one thing I need to add, which I'm realizing with this formula, which I did not add, is this over here. And I'm gonna quickly put it up for you, and it's this over here. It's actually equation 11.3. I just want to tell you that your stress concentration. So this was modified. Yeah. So it's the same formula, but now what I want to say, the only thing now is that we have it divided by KF over here, right? And guys, remember the P, which is your pitch, is inverse to that module. And I think I should just recap and show you so you can see your diametrical pitch. So don't be overwhelmed by that over there. Okay, so I'm just gonna paste so you can actually just see. So 1/P is module, or you know what I mean, or inverse or whatever. Yeah. I hope everyone is with me here. So that's the equation we're gonna use. Yeah. Okay, cool. Because anyway, we are just accounting for that stress concentration factor. So we're just gonna substitute. So what I'm saying is you just substitute the values as easier, right? So you're gonna say 172, no orders of magnitude, right? You times it by let me just zoom in again. Yeah. You times it by the width, which is obviously the 45. And then it's going to be Y, which was 0.42. And we times in that guy by the module of 2. And we simply divide by the KF given of 1.5. This is typically standard. That's a good approximation to have. And that's all. See, so no 10 times the power 6, no, changing it from meters to meters. You're just putting the values exactly like this. I'm not sure how that works, but yeah. So let's quickly get that bending force for me. You can just get it for me.
I got 4,148.64.
Okay, Tony, just give me, you said 4,100
48.
Oh, 4,000?
4,148.
Okay. Point
64.
64. Perfect. That's newtons, no? So that's allowable bending load, guys. That's what it is. Okay. That's perfect. I hope everyone, it's as straightforward as this. So remember now we've got A, and now we need B, which is the maximum tangential load, right? And power that the cake can transmit. So that's B. So we need FT. Now, unfortunately, we don't have a meshing system, that thing, and then we can find out FT with like that, depending on the way it's rotating and our radial load. We have none of that information here, okay? So what they're saying in this particular question, that they're making FB and FT equal, or FD equal, right? Because this is the limiting value. So what it basically means is that that's like the max value that FT could be anyway. Well, not the max, the minimum value, because I mean FB can be way greater than FT. So all we have to do is set FB equal to FD. But now let's find FD, right? So FD is equal to, and like I said to you, it depends on, and this is very important, your dynamic load or effect. All depends on your pitch line velocity and your tangential load, right? Obviously, other factors. But the equation, or I have that, let me just go to my slides. I'm just scrolling here. You need to now obviously find the velocity first. And then based on the velocity, it will then tell you now, okay, let me just place it here for you. Yeah, based on your velocity, you have to now obviously choose the right one. So the first thing to do before we do FD is find V, okay? So let me just erase my FD and let's find our V first. Okay. Again, the procedures that don't change for this thing, man. Straightforward. So V will be pi the n over 60. Colleagues, what do we have here? How do we find, we have n, how do we find out D? Who can tell me? What's the main value for gas? I just mentioned it in the start of the lecture. The main geometric thing. How do we find D?
We use N.
Module. Yeah, which is your diameter divided by number of teeth. Right? Always remember that one. Very important. So let's quickly find D using this one. Yeah, so you have I believe you have the teeth number, and I believe you have the module as well. You guys can tell me what D is.
Isn't it 50?
Yeah, but it's 50 exactly. It's nothing more, nothing less. It's 50 more, right? It's 2 times 25. Once that is done, we're just going to say pi times 0.05. And our speed was 900 revs per minute. That's all right. And you divide that by 60. And then you get...
Sorry, sir.
Yes.
When you were saying module, what is module?
Module. I explained
Yes.
it in the start of the lecture. You must.
Oh. Sorry, sir.
Okay.
Just misconfused. Thank you.
Okay, cool.
Thank you.
Module, yeah. It's the ratio between the diameter and the amount of teeth, yeah, in simple words. Okay, so let's get that pitch line velocity.
2.356.
Okay, meters per second, right? Thanks to me. And then based on that, you now have to check which dynamic load, and you'll notice it depends on your pitch line velocity. In this case, be between 0 and 10.16. So that'll be our FD. So what we're doing here, we're taking our FB, right, equal to FD. Sometimes, like I said, you have to calculate each of them individually, right? And then you're comparing the two forces. So that's in this case, they kind of just saying what is the limiting value. So FB was given as 414.864, I think, if I'm right. and we're making that equal to, I believe we're using this one, right? Because we're in that range of that. So I'll just put it here. So it's 3.05 plus 2.356 divided by 3.05. And then we're solving for FT. And FT is the thing that I want, the maximum tangential load and power with the gate transformer. Okay, so let's quickly get FT now. Power should also be easy. Yeah.
I got 2,340.
Okay, just give me a second to me. You said, yes, you said 2,000?
340.
340. That's fine.
613.
613, no? Okay. Once that is done, power, like we all know, should be FT times P. And we can find that that minimum, that power based on that force. Yeah. So yeah, that's basically it. It's not too much, really.
It's 5.51 kilowatts.
Thank you, man. 5.51 kilowatts. So here we just establish how much power can that gate transmit. Which is amazing. So again, this is very, very specialized gate design. Yeah, it's not a common thing anymore. Okay, so we've done that. I believe there's no questions. If there's any questions, then we can move on quickly to the where part. Any questions, guys, with this one? Okay, let me come over here. Okay, cool. So let me just share my slides again. And now we're gonna also make a new section. We're gonna move on to the where. So I'm obviously doing a bit different from the book. But it's you understand it's kind of flows better like this. So like I said to you, I'm assuming you guys can see my slides. And we will come to it now. Yeah, so in this case, we were looking at something called where, and instead of the Lewis formula, we're looking at the Buckingham formula, right? And this, again, the way what you're looking at when we design the gate, it's basically surface failure of the gate, right? Like I mentioned, the one of the other modes of failure, which you're checking for, okay? And what is just important over here is the following. The wear would be equal to your diameter, your pitch diameter times your width times something called Q, right? And then something called K, right? Once you have that, you then compare FW to FD again, just like we did before. So it's exactly the same type of thinking. You know what I mean? As the previous yeah, but now I'm just looking for where. Cool. So how do we get this value? So what's nice, our Q value, I want to just quickly show you our K value first, which talks to your surface endurance limit and wear factor, which is K in this case. Well, also it's based on your material. You pull up the endurance factor or limit over here. I'm sure you guys are familiar with where that has come from. And then depending on your material and the hardness thereof, you're able to choose your K factor. Now, your Q factor, just go to it for you. It's obviously, as you can see, it's a simple, straightforward equation over there. And so, yeah, I mean, there's not much to talk about there. But it's a straightforward kind of plug and play type of thing. But it's coming from like the maximum contact pressure. There's a few things, but don't worry too much about that. So what's key is just to know to pull where K's value comes from, and then obviously to get Q. And so the main formula is this one over here. And we're just gonna find that. So luckily K, in this case for us, we don't need to compute K. Like I said, we're just gonna pull it from this table. However, if they do give you, I don't think they do, in this textbook, endurance limit. Based on endurance limit, you're able to obviously get your K values, but I doubt that's the case. So let's try 11.7. Right? Also super simple. And now so now they're saying the opinion of 11.6, which we did before, is to be made to do the K. And what we're going to be doing now is we're going to be checking on that opinion in the previous example. We're going to do the allowable way for the K set and using the Buckingham formula. And then we're also going to do the maximum load transmitted. So we do exactly the same before, but we're just doing for this thing now. So let's quickly do this one as well. Cool. So I'm going to just go to the OneNote again, and we're going to solve this one as well. So I hope everyone's following. What we're doing is just checking for where and what is this? And where and bending. Okay. It's just a lot of tables to pull from. Okay. Cool. So here we are. We've got the previous one, and we now have to check for where. Okay. So let me just get the formula for you as well, so you can actually see it. And then we're gonna, yeah. Okay, I'm just gonna copy over here, so we can just paste it or push it over here, right? So can you see it gives you, it tells you DP, which is the pinion, right? We have to check pinion. And there's also a design decision of the mating gear. It's a 60-tooth cast iron. So obviously that is important. All right, so let's quickly try and solve this one. So FWA is FW is my wear equals DP PQ and then K. All right. K is the only value, right? We need to get from the table. So let me write that down for you. K from table. Okay. Q is equal to that over there. All right. So I believe everything is given to us. We have our diameter of pinion. We have our breadth of 45. We need to find Q and we need to find K. So let's quickly compute Q using this formula over here, guys. Let me just write it down for you. So Q is equal to 2Ng over NP plus Ng. Okay. So yeah, so let's quickly get Q. It's some factor which I'm not sure, man. I need to look at Shigley to give you a proper answer. Can I just get the Q value?
Q is 1.412.
1.412. Okay. What was that now? 1.412. Okay. Cool, right? Once we've got that, and then, like I said, the next value we have to get is our form, the wear factor K, right, from the table. So I'm just gonna get it for you so you can see. Okay. Again, pressure angles, all of that's important here. So the 1.412, no? So write that down properly. It's not tough, man. It's not tough. Just never mind, never mind. Just make it small. Okay. There's a lot, something what's different in this gear design from what I remembered, but anyway. So let's quickly have a look. So K, right? K is from the table, and we are looking at a 60-tooth cast iron gear, right? Cast iron. So if you look at this is both the materials in the pinion and the gear. So what I'm understanding is what was a pinion and what was a gear? Let's have a look, colleagues. Let's call remember now. Pinion was SA 1040 steel. Okay, that's not there. But what was its hardness? What's SA 1040 steel, guys? Let me have a look. I guess we need both. It kind of makes sense. I'm looking for the hardness. The hardness for that steel was 200. So SA 1040 steel was 200. Okay. So for pinion, it was 200 per now hardness. Not sure if you guys have ever done a hardness test before. I'm just going to show you now so you can see what I mean. So make a note that you're checking for both materials over here. I didn't want to mention it before, but I thought I'll show you now. So SAE 1040, the value there, average per hour hardness of 200. Can you see there? Cool. So if that's the case, your steel is 200 and our gear was cast iron, right? And if that's the case, we can say our TAFE factor for a 25-degree, can you guys see it there? Is 1.04, yeah, 1.014. Are you guys with me? If not, please tell me. Can you guys see it?
Yes, sir.
Yeah.
Yes, sir.
Perfect. Okay. So just remember, we're looking at both pinion and gear, right? That's what's key over there. Cool. So in that case, K was 1.014. That's nice. 1.014. All we do now, guys, we plug in our stuff. Straightforward. DP was given as 50. And again, with these formulas, there's no orders of magnitude. We're just plugging values straight away. 50 times B, the width was 45, times Q, which was given as 1.412, times K, which is 1.014. Let's get our way.
3,221.478.
3,221.
21.
21.418.
478.
478. Okay. And again, the maximum load that can be transmitted is exactly as, are you sure about that? Oh, yeah, okay, yeah. All we have to do is exactly as before, right? And if you recall, we have a condition of FW must be equal and greater than FD, because it's the same gearing set. We've got the pitch line velocity already. We apply exactly the same setup over here, right? So we're going to say the same thing, but the only difference is FW is over there. So now we're going to take this part, and we're just going to add it there. So it's the same. So it's going to have 3,221.478. We're making that equal to the 3.05 plus, what was it now again? I write it down here, 2.3356. Divide that by 3.05, and we're going to have to solve for FT. And that'll be our what is this thing called? Our maximum load that can be transmitted. Okay, let's quickly do that. See what you get.
I got 1817.5.
1817.5. Think 2 million, I should say big numbers. Okay, yeah. I'll just park it here for a second. Is everyone following? I give 2 minutes for digestion. It's not tough. Just some equations and stuff one must follow. Is there any questions?
No, sir.
Okay, I think that's straightforward, no? So what I want to do next is the following. Okay. Let me just go to the textbook first. So guys, what I want you to be practicing is this, and I'm being very, very direct with this. I'm just going to the textbook quickly so you can see. So if I go to this, now there are two approaches is of utmost importance. You'll notice a lot of them are presented here, but let me explain to you how you must tackle this. So you see all these gas sets over here. You know that they ask you the standard stuff of the forces, tangential, radial forces, whatever, the action of the shaft. You understand them. And then if you look at sections 11.8 to 13, that's what we're doing. What they will say is that for the gas sets 11.20, right? These ones, this figure, right? They want you to now find the allowable bending load using the Lewis equation. Assume Kf to be 1.6. Find the allowable load for wear applying the Park-AM for load, which you just did now for case 1 and 2. Then the maximum tangential load that K2 can transmit. So can you see how they incorporate both these ones? Can you guys see that? 11.23, they give you the same thing, but now they just change the values now. All right? Can you see there? But now they choose K3 and K4. Now, what I'm trying to say is that if you can go over all of these ones, surely you'll be sorted for the what do you call it, for the up and coming final. Then there's a slight modification, and that's coming with the AMGA method. Is everyone with me on how this works? Can you see how to tackle the problems? Yes or no?
Yes, sir.
Yeah, so it's not tough. So when you're expecting a question, it's going to be done like in one big section, like one bulk type of. Even though the tutorial I'm giving is I took one of these ones as well, but like be conscious that that's how it's going to be. You do the forces, and then from the forces, there'll be an add-on for this part over here. So that's just my advice for you to make sure you on the right track. It's not tough. It's simple equations. Just got to know where what is and things like that. But okay, let's quickly move on. We're not done yet, unfortunately. Now, the next piece is the following. Okay, so let me open up a slide over here and just where's this one now? And I can just write this down. So we talked about gear design, and we've established the failure bending, and there's another one over where. Obviously, there's the Lewis formula, right? And then you have the Buckingham formula, right? We've just done. So both these methods, right, come into something called American Game Manufacturing Association. These are like the international standard approaches for designing games. So this is for me. So what we're going to be looking at is, I think I'll try to do bending. So basically what I'm saying is that the Lewis and the Buckingham forms like the foundation for them. And you'll notice it's a similar thinking when you're doing helical or bevel. I think by next week we'll do helical. Yeah. So I'm just letting you know but it's the same. So let's go over this AGMA method so you can actually see what I'm talking about. Okay. Where am I? Okay, yeah. So designing for bending is the AGMA method. And guys, again, long story short, it's a formula with a lot of factors, right? So we've got this formula over here, which will be the so-called bending stress or the design stress from the gear. And then we have the allowable stress, right, which is this one. And what is key here is comparing the two. So if saying as design specification, the bending stress, which we find over here within our gear, right, it's nearly the same as the previous one, must not exceed the allowable stress, which is based on that value. So all it is here is finding those two values and making a comparison. That's it. So what are all these factors? Let me quickly, don't talk too much about it. I think we should just solve and then just kind of populate accordingly. But I do want to I made a note here and I want to just mention to you, like how these factors, so if you group these factors over here, so these ones, those ones, and those ones. These ones are, okay, let me actually just do it like this rather. Yeah, so this here is like, that's all to do with the load, all right? The load and each respective factors. Let me keep it, I'll come over here. These ones over here are the geometric ones. And these factors are talking to now the tooth factors. Okay. I could just group them. So on FT, the load factors, there are two things you have to add on, is an overload factor and a velocity or dynamic factor. It's all over there, all right? Where does it come from? Probably from some table or some graph. Just know that. Then we have 1 over B times M, which is simple, which is the face width and the module given. We're all familiar with that, right? No problem. Then we also have our Ks, which is a size factor, Km is a mounting factor, and dividing with some other geometry factor, J. That you're all going to find on some table or it might be given, right? So that's how it's going to work. Again, we're just adding all these additional factors for a variety of reasons. Then for us to compute our allowable stress, we're basically just looking at your bending strength factor, which will be times by a life factor divided by temperature factor divided by a reliability factor. All again, these are coming from graphs and tables. The long and short of it. Okay. Just to show you a few things. These are the bending strength of different gears now. So if I look at, where's this guy? That will be that ST over here for the allowable, just as an example, right? The table I was at. Here's this one would be the overload correction factor. This is again to do with, it's uniform, light shock or medium shock. We have to adjust there. We have put in a factor there. Again, I'm not sure where these factors come from. I just established somehow, I believe. I like to leave it to some kind of testing. Our dynamic factor in this case is a bit more tricky. It's exactly what we had before. We have a pitch line velocity, and depending on how the gear looks, you're going to have to obviously obtain a dynamic factor. But in fact, depending on which curve you have, we obviously have these nice formulas which can assist us with the dynamic factor. The mounting factor, again, that's how it's mounted, right? And the face width will tell us exactly what to choose. What else is there? We've got the reliability factor. Again, I'm sure if you've done fatigue, we should have done design 2, talks to that as well. No bearings, we mentioned that. So again, all we're going to do is, now let's tackle this example. It's a case study using this. And what I'd like you guys to do is, I'll just show you the textbook now. Quickly go over here. Let's just go, is to go over 11 point, where's my AGMA? So you can see here, your AGA method. There's a nice case study over here, which I'll try to quickly do today, which is this one. Go over this, right? And then you'll notice also for the where, there's another one as well. And there is also another case study for that one, which is just over here. Okay, so I'll probably go over this one now, the bending, and you guys can go over both the bending and the way. So I mean, I need to go into helical gears, but it's not tough. And so let's quickly try and do the AMGAM method now. Okay. So it's not, it's a lot, but it's not too bad. Just gotta know where. And I like this question because it's a decent case study. And again, this is the same approach they use. If you look at your project, it's exactly the same when they design the gauge systems. How they actually, I think next if the ones are not going to make it this time around, I'll probably do a gating system next year when I teach the subject. Okay, cool. So let's quickly do this. So you have a conveyor drive involving heavy shock torsional loading to be operated by an electric motor, turning its an RPM so much. Speed ratio of the spur gears connecting the motor and the conveyor or speed reducers to be 1.2. Determine the maximum horsepower that the gear can transmit based on bending strength and applying the engineering force. So that's your keyword over here. Right? Okay. So on the maximum horsepower, and they want, based on the engine. Okay. So what I'll do is just pull that equation so you can actually just see it again. And I'm just gonna populate them, right? Okay, I'll put the 1 year. Okay, so I guess it's not a comparison. I believe we can still do the comparison though. But that FT is obviously needed. We need FT, right? So I think in this problem, we're not checking the strength of the gearing system. We're going to need to solve for FT. So that consequently means that we need to find out our allowable stress first. And it's again based on that, we're going to have to make them equal to each other. So what I'm saying is we're going to make the allowable stress equal to the bending stress found, and then we're going to solve for FT. So that means we need to find the allowable, and we need to find all the other stuff over here. Oops. And then we make it equal. Then we find FT. Once we have FT, and obviously we can find, you know what I mean, all the other stuff. So let's quickly see. Let's try to find, I'm just going to go with the textbook. Let's try to find our allowable stress quickly, right? We'll start there. So your allowable is equal to ST times KL, KT, KR, reliability temperature factor, and your the loading factor. So let's see what we can get. Both gears are made of 300 Brunel steel, and let's see us getting all these factors. So what I'm going to do, I am going to get each table out, and so we can actually see Yeah. Okay. Yeah, let me just find okay, let me just go back to this first one. And again, these tables are provided for you, man. So don't feel overwhelmed. Just make sure you understand your approach and from which table it comes from. Okay, let's quickly see here. For this one, we are dealing with 300 Bernal steel, right? So where is that? It's probably quench and tempered, I'm assuming. And you guys
Sorry,
agree with
sir.
me? Yes.
You're not hearing, sir.
What am I sharing?
You're still on the book.
Okay, sorry about that, guys. Yeah, thanks. Let me just, yeah. So I'm just getting back. So what I was saying, guys, with this is that that's my bending stress, that's my allowable. And what you're probably going to do, we're solving for FT. So that means you're going to make the allowable equal to the bending stress. So yeah, so what I'm doing now is computing the allowable. So what I'm looking for, we have 300 Bernal steel, right? And we need to now obviously yeah, get KL, KT, KR. Yeah, okay. So do you guys agree with me that it's in between the range of 248 and 324? Are we happy with that?
Yes,
We all see
sir.
that? Yeah. So what you then do is instead of taking those values, let's find the average of them. Is that fine? You can do that. I think, yeah. We could have also chose the highest one. That is also kind of acceptable. But just get the average for me of those values quickly and see what you get. Just to make sure I'm doing the right thing here. Yeah. What's your average value for that one? Yeah. I got 286 colleagues. So I'm just gonna say a note here. 300 Brunel, and then I'm gonna say 248 plus what is it? 324 divided by 2. And I think I got 286. That's 286, right? So you put that there. Are we all happy with what I've done? Okay. We're just assuming an average value. We could have chose, normally when I chose the lowest value, you know what I mean, to 248. Colleagues over here, nearly done, nearly done.
Sir. Yes, sir.
Yes. Okay. Thanks, Bridget. Once that is done, we need to find this KL, KT, and KR, right? So what I'm going to do now, I'm going to share the textbook, and I want us to quickly get the values from there. So instead of me moving back and forth. So I'll show you exactly what it looks like. So this is where we can actually discuss. Cool. So here's my KR, that's my KL, and here we're talking about our KT. So let's just quickly look here. So I'll mention the temperature factor just quickly. And you'll notice the temperature factor, I'll just have it over here, is applied to just for the allowable stress for the effects of operating temperatures. We have done stuff like this similar before in fatigue. And they say for temperatures less than 71 degrees, KT is 1 is used. If it's greater, we then have to now obviously adjust. So now in our case, and this is for the lubricant temperatures, in our case, they have not stipulated anything. So we're assuming that it's going to be operating less than 71 degrees, like a normal environment, or the lubrications in a normal environment. So therefore, our KT is 1. So just make sure you write that down. I'm writing it down here by me. After KT, we need to find our KL, which is our life factor as well. Our life factor is given over here. And based on this, they talk about the amount of cycles. So I'm not sure they stipulated the amount of cycles. And it's all dependent on the hardness. So obviously they should have stipulated amount of cycles. We could have possibly interpolated. Can you guys see that for this one? So okay, I'll just put a pause for now. Just check what they did. So then we have our reliability factor, and the question stated. Oh, here's the question. Let's have a look. I think they assumed values. Am I right? Let me just check. 286. They say one. Oh, they said one for indefinite life, one for there, and was our reliability given? No. So they've also assumed in this case a very high reliability. So in this case, they chose 99.9. So it's 1.25. Again, this over here, typically in a question, it will be stipulated, right? If not stipulated, it's a case of just substantiating what you chose, right? Yeah. All right, guys, are we all there? And then let's quickly reverting back. It says for a life factor, like I said, depends on your hardness and that. But in this case, let's say it's indefinite life. So this is probably is this the best? So 10 to the power 7, you're just going to go with a 1. So okay, I'll use 1. Okay, so in this case, it didn't specify. So we're just going to specify ourselves. But normally, typically, if it's a case, they'll tell you it's this, it's that, it's this. Okay. So then coming back here, going back to my OneNote, and then I'm just gonna quickly go here. So as I have there, my KR was 1. That was for indefinite life. Our temperature factor was also 1, less than 71 degrees. And then the KR is 1.25. That's the reliability factor. Okay. Can someone just get me my allowable stress for me? Okay. Should be a quick and easy one.
228.8.
Guys, are there any questions? Anything unclear? Aiden, Bridget, Fabio, Morgan.
It's 228.8.
Can we just get that? How much? Bridget?
228.8.
228.8. Like this. I think that's what you said. That'll be in megapascals. Okay, that's perfect. So once that is done, the next step is obviously to do a similar thing with all of these over here. Okay, so now we just take that, paste that over here, and let's just see where we get. So what we're going to do is we assume that our allowable is equal to our bending stress. So that's going to be the limit. So we're going to find FT. But now we need to find your KO, your KV, B and M is your module and your breadth that's given to us. So that's done. Then we need our KS, our geometric factors, I believe, in KM and KJ. So let's see our KO and KV. Okay, so let me just go back to the textbook so you can actually see what that is. Yeah. So a lot of the gear design, it's exactly like this. I mean, as you can see, it's just pulling tables, putting stuff in, not tough. KO, right? Again over here, KO. Did they stipulate for us? Did they stipulate for us our overload factor? Right. So let's quickly go look. I'm looking at the question. and they don't state anything, right? So we have a conveyor drive, oh, with heavy shock, torsional loading. Okay, so heavy shock is a keyword, and therefore conveyor heavy shock should be around 1.75. You guys with me there? Our KO is 1.75. Colleagues, are you with me? Can I get a yes?
Yes.
Okay, cool. And then our velocity factor, right, which is the dynamic factor. Okay. And again, that's to do with these ones over here. Okay. So we need to now obviously have a look at these and see what is best. Obviously, oh yeah. So now we first need to find our velocity. That's also key. So I think we'll do that. But let's first determine where, oh, based on our, okay, yeah, based on our velocity, then we're gonna also have to have a look. So let me just look here what they state. Just reverting back to the question. Okay, that's gonna be our velocity. Let's have a look. Both gauges are 300 per now steel. And I'm just looking. Okay, let's just see 300 per now steel. And based on that, okay, so I mean, it's not what should be stated is high precision shaved and ground. That depends on the way it was manufactured, right? So I'm just going back. Does it tell us about how it is manufactured? No, right? So in this case, I mean, they surely should, but anyway, so that makes it a bit tricky. Horsepower, yeah. So that's another assumption that we'll make, right? So we're gonna have to assume this should have been mentioned. This must be mentioned. In exam, it will not be that unclear. So in this case, they're saying it's precision shaved in ground. So we're going to use curve C in our case. But I do want to make you aware, also is they say V is in feet per minute for these equations. And to convert 2 meters per second, we must divide the values given by what is this? The 196 point. Yeah. So let's quickly, based on curve C, we're assuming, I'm gonna write it down here. So I'm just finding our KO is given as was 1.75. That is the heavy shock. And then KV, I'm gonna say over here, I'm gonna come back now there to precision shaved. That's precision shaved and ground. Okay, I'll just say curve C rather. Curve C. I'm just getting the formula for you guys. We'll get back now. So it's 3.56 plus root. And yeah, I think it's they're leaving it open because it's hard to exactly say. Yeah. And this is why we keep these stuff for the projects, not for the exams. Okay, cool. So let me just go back. So I'm going to end it off here with finding KV, and then you guys can do the rest. Okay, so let's get our velocity, colleagues. Our velocity is pi d n over 60. And again, it's just we can easily find that there. Module number of teeth, we can actually get the diameter over there. So we know that your diameter will be equal to module times teeth. And that is going to be for the pinion, no? So NP, so that's NP, so that's DP. So that's going to be 2.5 times 18. Okay. Hope you guys are with me, eh? 2.5 times 18. I think a lot of people are uncomfortable that it's not specified. So we have 45. 45. So that's 45 millimeters. And we can easily now find a velocity based on that. Okay. So if you find the velocity, you should get 3.77 meters per second. And like I said, these equations works for feet per minute, right? And therefore we must now divide we should times by 1.96. Can someone just get me the kV value, please? Yeah. Yeah. So this must be converted into feet per minute, I believe. Okay. Can someone just give me that in feet per minute? What was it again? 3 point. Colleagues, are you guys still there? 3.77. I think it's 742.13 now. 742.1. So we take that value and I believe we just put it in here. Okay. Okay, guys. Is everyone still good? I'm not hearing anything. Lucio, Tumi, Morgan, CJ. Yeah.
Yes, sir.
Okay, cool. So I'm just gonna, if you put that value, I'm not sure what value you're gonna get there, but put it in and then get that value, and then just you can obviously just do the rest of the question. I think I'll probably continue with the last of this question, just to make sure I went over the AGMA method. And then there's also the where, but don't stress too much with the where. As long as you know your Lewis and Buckingham for now, that's great. But complete this one. I'll finish it, and then we're gonna start on helical gaze next week. Yeah, but next week, Tuesday, I'll be in a workshop Monday and Tuesday. And so, yeah, I'm probably gonna have to see you at another lecture again in the week. But Fabio, yeah, it'll be nice if you can just with the class to determine. Yeah, but anyway, guys, thank you very much. I'll share the link again, but just make sure you go over that exercise that I told you in that way. The forces, Lewis, Buckingham. If you can do that, you'll be A4 away. Okay, guys, thank you very much. See you soon on campus. Cheers.
Thank you, sir.
Okay, thanks, man.